All right, so ladies and gentlemen, welcome back. This is part two. We're still talking about series circuits. So we just discussed kind of the rules for how current and voltage work for a series circuit. We talked about the idea that if you have a circuit that is in series, just the idea of loop rule, that the current is going to have to be the same through that loop. It only makes one loop. The current is the same at all points. The second piece of this is the idea that you have a voltage drop. Okay, and that's just the idea that basically as electrons go through light bulbs, resistors, whatever is in the circuit that's kind of drawing energy, it has to actually drop some voltage as it goes through it. And it has to drop the same amount of voltage by the time it gets to the end of the circuit that's equal to whatever the voltage of the battery was. Okay? And the best way I can think about visualizing it is the idea we've talked about, that the fact that voltage is like the height of a waterfall. All right? And we can think about these voltage drops as a waterfall that maybe is falling into little pools. Okay? And maybe it's several waterfalls that eventually gets all the way down to the bottom. All right? And the voltage drop kind of is affected by that. Okay? So you can have small voltage drops, large voltage drops. It doesn't, just depends on the object. All right? But what we will say is that it takes, the voltage drop is greater if the resistance of the object is greater, because we're going to find out it takes more energy to get through it. Okay? Now, our next piece is talking about what happens when we have multiple resistors in series. Okay, remember, resistors are literally exactly what their name is. They are just objects you put into a circuit that basically slow down the movement of electrons. Okay, and they can also be light bulbs as well. All these things provide resistance, so they're resistors. Light bulbs just have a very specific function, so they get a very specific name. Now, if I have a circuit where I have multiple resistors in series with each other, right, I can either look at them as individual resistors, and that would be fine, but I also can do something that we've done several times in class, and we do a little magic. And what I can do is I can look at these three resistors and say, let's say I'm standing really far away, and I've also put a magic box over these resistors. All right? What we're going to find out is that according to the electrons, they can't really tell what's going on if there are three resistors or not, especially if we have this magic box over there. But what they know is that they have to drop off energy every time they go through these resistors. All right? Now, when they're in series, the current all flows through it. So that means the river basically has to flow through all of this. All right? Or you can think of it like kind of a toll road. All right? Each one of these resistors is a toll booth, and you have to pay a certain amount of money to get through it. In this case, the electrons have to pay energy to get through it. All right? Now, I can either break it up, and my electrons can play a little bit of energy here, a lot of energy here, a medium amount of energy here, and get all the way to the end. Or you could reimagine it as, instead of it being three resistors, I can imagine this as one much larger resistor. All right? And instead of paying three separate tolls, I just pay one much larger toll that's the same as the three together. All right? And that's what happens when you put resistors in series. If I put resistors in series, what happens is they act like a much larger resistor. All right? And that's because if we put an imaginary box around it, you can't tell if there are 3, 30, or a million resistors. You just know that they're all acting like one much bigger one. All right? So in this case, for resistance in series, all right, if resistors are in series, we can add up the resistances and just treat them like they're one big resistor. So because of that, what that means is that if I look at the example, and you have the example up here, that's where I pulled this from, all right, I've got three resistors all in series, which means if I want to treat them like one bigger resistor, maybe I just want to simplify what's going on. Because they're in series, the resistances add together. So in this case, R total is just going to equal R1 plus R2 plus R3. So R total for this circuit, or you can call it R equivalent. Actually, we'll do that. It's just going to be equal to the three things added together, which in this case is 450 ohms. All right, and just in case you're looking for a formula for this, basically for resistance in series, REQ, the equivalent resistance, is just equal to R1 plus R2 plus R3 plus da 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 all the way up to Rn, whatever number you choose. All right? So, if you can, take like 15 seconds, answer this little question. So resistors are in series, they act like blank, where we blank the resistances together. And then honestly, the fill in the blanks are kind of up to your own choosing because there could be different things. But basically, we're going to say that if resistors are in series, they act like one larger resistor where we combine the resistances together. All right? Now, this is a very important piece for series circuits. All right? And this governs a lot of things about what's going on with them. So, as we start throwing more and more things into a series circuit, and this is one of the biggest downsides of the series circuit, all right? The total resistance of the circuit is going to change. And just think for a sec what might happen if I start throwing more and more things in series with each other in one circuit. All right? Hopefully when you thought about it, your first thing was like, ooh, the resistance is going to start going higher and higher. All right? And if I do that, if the total resistance starts to increase, so if we add more and more objects into the series circuit, the total resistance increases. All right? And if I don't change anything about the voltage, if I'm still using the same battery, what's going to happen is the current going through that circuit is going to get smaller and smaller and smaller until eventually it's going to look like no electricity is flowing whatsoever. Okay, so if total resistance increases, if voltage stays the same, the current will drop. All right? Now, what that looks like is exactly what you would expect. Let's say I take this battery and I put a lot of light bulbs. I'm gonna get rid of a ton of light bulbs. I'm gonna move a bunch of light bulbs in here. All right, so I got 4, 5, 6, 7, 8 light bulbs. All right, we're really not messing around. So I got 8 light bulbs. I'm gonna connect all of them up. Of course, it's gonna take a hot second because I gotta put a bunch of wires in here. But what we want to pay attention to while I am setting this up is kind of look at what the original brightness of the light bulb is if there's only one. And look how fast the electrons are moving. Now, as soon as I connect all of these, look at the brightness of those light bulbs. I mean, there almost isn't any. You can barely see a little light coming from them. And look how fast those electrons are moving. Trick question. They're barely moving at all. All right? There's still current because electrons are flowing, but because the resistance of all these light bulbs in series is so high, very little current can move through. All right? And in this case, we get the situation where it doesn't look like anything's happening. All right? Now, for us, one of the more important reasons why we kind of talk about circuits is because honestly, all circuits are a source for energy for things that we use in daily life. All right? Specifically, they're a source for power. And remember, when we talked about energy, we talked about power. All power is how much work I do in a certain amount of time. So electrical power is basically how much energy am I giving to an object that it can use in a certain amount of time. All right? Now, for us and for a circuit, any object that an electron is moving through requires power to move that electron through it. All right, so just what we can say is each object in a circuit requires power to move the electrons through it. Okay, and there is a formula for this. We're going to talk about it not in this next video, but with the next kind of classwork we're going to do. Because you can literally calculate how much power different parts of the circuit uses, which is very important because sometimes you need to know exactly how much power is being used by certain pieces, all right, in case you're trying to maximize efficiency or you're trying to make sure you're not going to accidentally destroy something, all right? So, with that being said, for series circuits, we kind of have a rough idea of how it looks. It's basically one long loop. Everything's on the same loop. The current through everything is the same. But as you go around, it drops voltage slightly different, okay, as it's trying to get back down to 0. And when it gets through everything by the end of the circuit, the voltage drop has to equal the voltage in the battery. Okay? So now, we started with the idea of a series circuit. Now let's talk about the second type of circuit that we care about. It's referred to as a parallel circuit. All right? Now, parallel circuits are slightly different than series circuits. And what I mean by that is that a parallel circuit does not just have one loop. Instead, it has multiple paths. And the way we can draw that is it looks like this. So for parallel circuit, we're going to draw our own little thing. So just going to go to insert. And insert a little drawing. And what a parallel circuit would look like would be the following. So let's say that I have, I'm going to start by just making a branch. Okay. I'll put a little, just a little circle. And I'm going to explain why I have these little units, these little symbols in a second. These circles actually represent in a circuit diagram, they basically represent light bulbs. And then I'm just going to draw the second part of the circuit. Okay. This is a symbol for battery, by the way, in a circuit diagram. Sometimes you see two of them next to each other. Still, it means the same thing. Now, right here, we have a circuit diagram. And this circuit diagram is quite important because this is a circuit diagram for a parallel circuit. Okay? And what I mean by that is that if we look at this circuit, you'll notice this isn't just one path anymore. All right? My electrons leave the battery and start moving up the path. But at a certain point, they reach a section where they actually have to choose where they're going. It splits. Okay? This would be equivalent of basically maybe if I had our river, there's an island in the river, and it splits the river so that part of the river goes to the left, part of the river goes to the right. Okay? Now, in a parallel circuit, we're going to find out that that causes some interesting things to happen with what's going on in each branch. All right? But basically, it's got, the most important thing with a parallel circuit is that it has multiple paths for the current to travel. So what we're going to, when we define a parallel circuit, it's just a circuit that has multiple paths for the current to travel. All right? Now, that means that actually it's governed by a slightly different set of rules than the series circuit is. And one question, I'm just going to check real quick what my time's looking like. All right. So we're going to answer this quick question, and we're going to end this video and go to the next one. All right. So it's a circuit that has multiple paths for the current to travel. This is similar. This is something what it looks like. It'll look like basically just a path that kind of has multiple things going around in a circle. Now, the most important question about a parallel circuit is this one, and that's what happens to the electrons when they hit a junction in the wire. Now, electrons can't just split themselves in half and kind of have half going one way and half going the other. They have to pick a path, all right? And what happens is that basically the electrons will pick a path, and they will try and figure out which pathway has the least resistance, okay? Because remember, electrons hate kind of having to do work, so they're going to try and find the path of least resistance. So in this case, that's exactly what happens. So what happens to the electrons when they hit a junction in the wire? They pick a path, you call a branch if you want, and travel through it. And they pick based on the path of least resistance. All right, or they look for the easiest path. Now, what I want you to do, and then at that point, and then I'm going to end this video and start the next one. What I want you to do is I want you to go back to the circuit construction kit. And I want you to try and build a circuit that looks like this, all right? And this will be kind of weird to think about, but I want you to try, let's try it out. Try and visualize how you can build a parallel circuit, all right? Now, I want you to still leave the other series circuit where there's just one light bulb in there, but try and build a parallel circuit and see what happens, all right? So that being said, this is where I'm going to stop this particular video. The third and final part of this will cover the rest of parallel circuits and a little bit what happens when we mix them together, okay?